This question is probably the easiest calculation we do this semester, but it's also very important for the way we classify stars. This time, we're calculating a star's surface temperature based on the light it emits. Remember that the name for the light emitted by an object because of its temperature is thermal radiation. So we're using thermal radiation to measure the temperatures of stars. There's not a lot of information the question needs to give, so we can move right on to the prediction. You're asked to predict which star has the hottest surface and which one is coldest. The easiest way to do this is to look at the column that lists the wavelengths of light emitted by the stars. Remember that wavelength isn't a measure of how much light the star produces. Instead, it's a way of describing the color of the light the star glows in, though in some cases these colors aren't visible light. Nonetheless, you can still use the basic idea about thermal radiation we learned in class. As objects get hotter, they produce shorter wavelengths of light. So you can use this information to make your prediction. The equation that connects the peak wavelength of light to the temperature of the object producing that light is called Wien's law. This is given by T equals 2.9 times 10 to the 6th nanometers divided by lambda. T is the temperature and lambda is the peak wavelength of light produced. The 2.9 times 10 to the 6 nanometers is a constant. This constant tells us what units we need to be using for the wavelength, nanometers. Note that this equation gives us an answer in Kelvin. We don't usually write the kelvins in the constant for historical reasons, though you can if you want to. This is really a very simple equation. There is just one constant and one number we need to put into it, the peak wavelength of light emitted by each star. So list those wavelengths for each of the stars you'll be calculating. Make sure that you include the two you predicted earlier. Notice that these values are already given in nanometers, so we don't need to do any unit conversions. You can leave that box blank. So let's go ahead and do this calculation. Simply replace lambda with the wavelength from the table and divide them to get the answer in kelvins. We'll do this calculation for a star emitting light at a wavelength of 210 nanometers. As we divide them, we see that the answer is 13,800 kelvins. Remember that our Sun has a surface temperature of 5,800 kelvins, so this star is significantly hotter than the Sun. Also, note that the question asks you, in what part of the electromagnetic spectrum this star is producing most of its light? Once again, the peak wavelength is the key here. Visible light runs from 400 to 700 nanometers. Long word of that is infrared, while shorter wavelengths are ultraviolet. Since this star's peak wavelength is at 210 nanometers, most of its light is ultraviolet. Now compare your answer to your prediction and decide if you've got it right. If so, say so here. If not, decide if the error is in the calculation or the prediction. If it's the prediction, explain what you should have predicted. One way to tell if the problem is with the calculation comes from looking at the values you're getting. Since you're working with stars, the temperature should be pretty hot. Anything less than 1,000 kelvins is likely to be too cold to be a star, and very few stars reach temperatures as high as 100,000 kelvins. So you should expect temperatures between those two values. If you're seeing something outside of that range, it probably means there's a problem with the calculation. Remember, if you're stuck, you're welcome to ask for help.